In the last video, I showed you how to do the two-way ANOVA with interaction effect, with replication and interaction effect manually, okay? Or if you plot the average of each of the columns, not the cells, if you plot the average of each of the columns and average of each of the blocks, okay, then you can kind of see whether there will be interaction or not, or whether the column means are equal or not, or whether the block means are equal or not in the population. Okay, you can kind of make some guess. Okay, so look at this on the example that we did where we had male and female, and then we had the hormone treatment and no hormone treatment, right? That's what we were doing in the example. So if you plot the average of the hormone treatment and no hormone treatment of male and female, then this is what we will get. See, this red line is for the male. So this dot is the average of the no hormone treatment male, the plasma calcium content of the no hormone treatment of the male. This dot is the hormone treatment average plasma calcium content of the male. So this is for no treatment, this is for treatment, and that red line is for male. And for this dotted line, the blue line, it is for female. Okay, so what can we see from here? You can see that the average of the male and the female for both no treatment and treatment are almost the same, right? Because they are like differ by very few number, very little number, right? So what you can guess here is, so the average of the male and female are equal, right? The average of the male and female, the average calcium content, plasma calcium content for the both male and female are equal for treatment and no treatment. Okay, and similarly, if you look at these two, see, for the no treatment, these are the average of the male and female hormone plasma calcium content, and this one is for the treatment. Okay, you see that is different, right? Because it was like around 15. Now with the treatment, it is around 30, right? Or between 25 and 30, right? This was between 10 and 15, and this is between 25 and 30. So you can see that the treatment type has impact, right? The treatment type has impact on the plasma calcium content. What does that mean? That means the average calcium plasma calcium content of the no treatment and hormone treatment are not equal. The average are not equal because it is different, right? Because it was low and it was high. You can see that. Also, you see that these two lines are kind of parallel but not really parallel, because you see that if you extend this long, they will meet somewhere, but they are almost parallel though, right? So you can see that since they are not perfectly parallel, what we can say here is there may be some interaction effect. Okay, so we will check, we will find out, we actually found out already if there was interaction effect or not, right? So we found that for the interaction effect, we found the p-value was 0.62, meaning that there is no interaction effect. Okay, there is no interaction effect. So we do not reject the A0. So there is no significant interaction. There is interaction effect. From here we can see that there is interaction effect because they are not perfectly parallel, but the interaction effect may not be significant. It may be just slight interaction effect only. Okay, that's what we can see from the plot. Let me read this. Since both hormone treated male and female have increased plasma cell concentration, we can see that treatment has higher impact on plasma calcium concentration. Okay, the treatment has higher impact than no treatment. So the average of the no treatment and treatment is not equal, right? And the next one is, since both male and female have almost equal plasma content, right? For male and female, no treatment and treatment, they are almost the same. So we can see that the gender has no significant impact on the plasma content. And then the last one is, since the two lines are not perfectly parallel, there may be some interaction effect, but that interaction effect may be significant or may not be significant. And then we found that it is not significant. We can guess from that plot as well. Okay, so the next thing I am going to do is I am going to show you how to do this directly, all these steps directly by R. Okay, that's what we want to do. Okay, let us try that here. So directly using R, first of all, I am giving a name treatment type, because again, as we mentioned earlier, we need a data column first and then treatment type column, the hormone treatment, no hormone treatment, like that, and another column is male, female, male, female, male, female, like that, right? So we'll need 3 columns here. One is for the data, real data. The other is for the one factor, that is gender. Another is another factor, that is basically the treatment type, right? All right. So it does not matter in which order you do, in which column you put those things. Okay. So what I'm going to do is I'm going to take the factor A as gender. Let me do that, factor A as gender, and then factor B as the treatment type. Okay. So treatment type, there are 2 treatment types. One is the hormone treatment and another is the no hormone treatment. So for the no hormone treatment, I am denoting this by no treat, right? And then treat. So how many are no hormone treatment? The length of F and T and length of M and T. So the female non-treatment and then male non-treatment, right? And for the treatment type, there is a female treatment treated and then male treatment. So that means that many of them. Okay. Now the gender is female and male. How many female? F and T. And then male, how many? M and T. Also, how many female in the treatment type is FT many? Because there are 5 in FT, there are 5 in MT. So if I run those 2, and then if I put them all in the same matrix, what do you see? You got that this is basically the plasma CC. So plasma CC is what? Plasma CC is the data for, you see that FNT, FT, MNT, MT. They are putting all them together. That is the plasma CC data. Okay. So that's what the plasma CC data. So we put all them together in a row. Now we want to put all these 3 things in a column format. That is, we will be using data.frame. Plasma CC is that. All these things will be along the column. And then gender is male, female, male, female. That is the factor A. And then treatment type is the factor B. That is treated, no treated, like that. Okay. Let us see how that look like. So what it says is error in that. Oh, there is a comma there. So I don't. So the R doesn't like a comma and then nothing after that. So that's what the data is. Okay, I denoted data 1. So the plasma CC is that values 16.3, 20.4, and those. They are all female, right? Female, 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 female. They are under no treatment. No treat, no treat, no treat, no treat. Okay. And then other 5, the second 5 are male. Okay, 15.3, 17.4, 10.9, 10.3, and 6.7. They are male but under no treatment again. All right. Similarly, these are the female of hormone treatment, female hormone treatment, and then the other one were male hormone treatment. So we put that. So what are those? Like numerical data or the factor data? What types of data are those? So we got plasma CC is the numerical data. Gender is male and female. So this is not numerical. There are 2 levels, male and female, right? And 1 stands for male, a female, and the 2 stands for male. Similarly, the treatment type has 2 factors. One is no treatment, another is treatment. So again, we denote 1, 1, 1, 1 by no treatment and 2 by the treatment level. Okay. So what we want to do is, if you do not consider the interaction, what do you get? And we will do, if we consider the interaction, what do we get? Okay. So first of all, since this is the 2-way ANOVA, we need to write treatment type plus gender. You can write gender plus treatment type. No worries. No problem. Okay. So I'm giving a name result 2-way ANOVA equals to that. So let me run this one and then see what do I get. Okay. So I got, and then I ran that and then summary of that result. I got that treatment type is significant. We found that, right? The treatment type is significant, right? We see that the treatment type means the factor B, right? It has a highly significant effect. But the gender is not significant. We got 0.0647 because which is greater than alpha, right? And we got the treatment type has sum of square is that, and mini square is that, F value is that. Similarly, gender has sum square, mean square, and then F value, right? And the residual is the error part, right? That is the within cell mean square and so on, right? And this is what we found, okay? And the 18 is the mean square, okay? So here I'm not considering the interaction effect, right? If you want to do the interaction effect, what you need to do is you need to do treatment type plus gender plus type and then colon, that double dot gender. It will count, it will talk about the interaction effect also. Let us see that. Let me run that line 594, and then if I run the summary, you see that treatment type versus gender, this is for the interaction effect. So interaction effect is not significant because we got p value is greater than alpha, okay? For interaction, sum of square, mean square, and then F value, all those we got exactly the same value when we did manually, okay? All right, so this is what we got. And then if you want to see the interaction plot, that means you see that the plot of the mean, this is also called interaction plot, okay? This is the plot of the mean. What did I do here? Is interaction plot. X factor is treatment type. Along x-axis, you will be doing the treatment type, and trace factor is the that inside the graph. Okay, so plasma CC is the Y level, which is the real value of the averages, right? And then we call trace factor. Trace factor is seen here. Okay, so trace factor one is the male, another is the female. So that is the gender is the trace factor. Okay, trace factor is data one gender, and response is data one $sign plasma CC, that is the response. Response is the y variable here. So function is mean, we will be presenting mean here. Type equals to B. What does that mean? That means it will be just, you will have a circle as well as the line joining the circles, okay? That is the type. And legend equals to true. Legend will be seen here, that's called legend. And X level is treatment type, Y level is plasma CC, PCH 119. So I think this is, if you change on this, it is just a cosmetic thing, okay? And then color is blue. So these are all the cosmetic things, so no worries about that. The main thing is X factor, trace factor, and response, okay? And the function. So these are the main things. Let me run that and then see what do I get, okay? So let me run that. If I run line 602, this is what I got. So exactly the same graph I got. That means that you will see the graph of the means, right? So that will be the plot of the means of each of the blocks and each of the columns, okay? So this is how we do using R. So usually whenever people do the two-way ANOVA, they also present this interaction plot, okay? Plot of the means also, okay? So this is not enough. What we need to do, we haven't done any of the we have not done any of the assumptions, right? What are the assumptions? Homogeneity of the variance, right? Also another assumption is normality of the residuals. We will do that, okay? And also if we reject the null hypothesis of any of those three null hypotheses, we will be doing the pairwise. So I'm going to show you those things, okay? So let us talk about the homogeneity of the variance, okay? So for the homogeneity of the variance, you can do, this is what you do, Bartlett.test plasma CC, and then wiggle sign, interaction, treatment type, and gender. Data equals to data 1. What do you get? You get that the p-value is 0.996, meaning the variance are equal, right? We do not reject the null hypothesis. You see that? And then there is another way, Flinger test, right? Flinger test also show that the p-value is almost 1, right? So we do not reject the null hypothesis, okay? So if you want to plot for the homogeneity of variance, what we do is, this is plot result dot to F ANOVA. That's what that value and name of that, right? Name of that is, and then I am plotting that one will be, it will be basically plotting the let me see, it will be basically plotting the residual versus the fitted. You see that? Whenever you see that this red line is the average of those, whenever you see the red line is almost equals to or almost very close to the dotted line, you see that the variances, you see the variances are equal for each, for it's what it says is for each x values, the y values are equally scattered around the mean, right? But we are doing for the residuals, that's why the residuals will have the mean 0. That is the reason why it is around 0, okay? So for each x values, the y values are equally scattered around the mean, or the residual y, the residuals are equally scattered around the mean. That's what it says, okay? All right, so for the test of normality of variables, what we do is we check the normality of the residuals, okay? So analysis of variable residuals is residuals and object that, and then we will be doing the Shapiro test is saying that the p-value is 0.31, meaning the variables are normally distributed. So normality test is not violated. If you want to plot for the normality, this is what you get. You see that all those data points are close to that line, so normality is not violated, okay? That's what we got. So those are the mainly two. You know you know what the homoscedasticity means? Homoscedasticity means for each x values, the y values have the equal variances. So you can see from here too, okay? You can see that because for each x values, the y values are equally scattered, right? That is, the y values have the same variable. Or here we are finding the residuals. So the residuals are equally scattered, or for each x value. So you see that they are this much scattered, this much scattered. All these for each x values, the y values are equally scattered. So you can see from here that the homoscedasticity as well. Okay, so the next is the 2K type comparisons. Okay, you see that male and female, I have equal, almost equal the average plasma concentration, right? But the treatment type and no treated and treated have the unequal one, okay? So if there are more than 2 levels, then the 2K HSD will show you the pairwise, okay? From above analysis, we see that ANOVA test is significant under gender. With that implies that the group means are not equal. That is not true, right? Because the male and female did not have the equal, so male and see, gender is not significant, right? Gender is not significant, but the treatment type is significant. So what I should say here, instead of saying that, I should make it a little bit correction there. That will be, let me see, where is that? So from above analysis, we see that the under treatment type, right? We do treatment type, okay, which implies that the group means are not equal. We now want to figure out which mean is not equal by using 2K test. Again, there are just two groups, there are just two blocks, right? Because we saw that the hormone treatment and the no hormone treatment have different means. We saw that, we checked it from here, right? Because see, treatment type has the p-value less than alpha. That means that it is significant, meaning that we reject the null hypothesis. So the mean are not equal. But since there are just two, we know that those two means are not equal. But if there are more than 2 blocks or more than 2 columns, then you want to find out, if you reject the null hypothesis, we want to find out which 2 are not equal, which one is the one that is different from the other, has average different from the other. In that case, we use the 2K test. This is the code you do. Result.to ANOVA, which equals to treatment type, and then that, and then gender. What you do, if you do that, if then look at this, treated female, no treated male, okay, sorry, treated female and no treated female. So it is, so treatment type has the significant, right? So it is significant. No treated male and no treated female is not significant. See, you see that the treated and no treatment are significant. You see that all those treatment and no treatment are significant. We find out that, okay? So this is what you see that. So what does that mean? That means you see that, look at this, the average of the treated female and average of the no treated female are not equal. Another one is the average of the treated male and no treated female are not equal, right? Average of the no treated male and no treated female are not equal, and the average of the treated male and no treated male are not equal as well. So treatment has impact on the plasma CC, right? Because the treated and no treated has the different averages. That's what we see that. Okay, guys. All right. So I will give you one more example, But before that, let me see what it says. When you do R, when you use R, then you can do all those with replication, without replication, even with replication. If each of the cell have different number of replication, R will do it easily. Okay, but the idea is similar if you do manually, but it involves more computation. So I just presented just two cases. One is no replication, other is the equal number of replication. Okay, if there are unequal number of replication, what would you do? If the cells have unequal number of data points, then the above procedure is not applicable. Unequal replication could be in rows or in columns or in both. Okay, there are two types in this case: proportional replication and disproportional replication. However, it is advised that you collect equal number of data in each cell. Usually we use statistical software capable of performing such ANOVA for such situations. Okay, all right. So things to remember: before you perform a two-way ANOVA, you need to check the assumptions: homogeneity of variance, normality of the dependent variables across each graph, and no outliers. The test is robust for mild violation of the normality. If the assumptions are not made, either you correct your data or use alternative statistical test. Also better to include them in the discussion. If there is an outlier, you can replace it with less extreme values or transfer the data into the other form, or proceed under the assumption that the outliers will not affect the analysis. And normality can be checked by using the Shapiro test. We did that, right? If not normally distributed, you can transfer the data or use the non-parametric test. ANOVA is robust for a small violation of the normality. That is the end, and then this will be the homework problem. Okay, I will mention that in the separate sheet of paper. Okay, so what I'm going to do now is I am going to present another example. Okay, another example for the two-way ANOVA. Another example for the two-way ANOVA. Let me clear everything on the console. All right. So let us do that. A two-factor ANOVA equal replication again. So I'm using just R directly. You see that? So so there is no difference of the mean of factor A. There is no difference of mean of factor B, and there is no difference between the factor A and B. There is no interaction between the factor A and B. So the data is the tooth growth data. So that it has three columns, right? Length is the number, and supplement is the factor, and then dose is number. Oh, we need the dose is also a factor because there are three factors there. 0.5 and then 1 and then 2, right? So what I'm going to do here is see that the dose is saved as a numeric. To change it into the factor, you do the following. So data 1 dose is equals to as a dot factor, okay, and data 1 supplement. Data 1 dose is already supplement is already a factor, so you don't need to do that, okay. But if you want to do that, just to make sure, okay. All right, and then if you run those two and then print the string, you got those two factors, and one is the variable. Now, so you know that this data is already given in the column format, right? You see that this data is already given into the column format there, so you don't need to write in the column format. This is already given. So length is the main data set. So the supplement is one factor, and the dose is another factor. Dose has three. Dose, let's say dose is the factor B. Factor B has three levels, and supplement has just two levels: vitamin C and orange juice. You see that? But dose has three: 0.5, 1, and 2. Okay, this is what you see. All right. So what I'm going to do is result. So the table. So table is data 1 length and data 1 supplement. I don't think you need this one. Okay, so you don't need this one. So let us not do that. Okay, so result 1, I'm doing the analysis of variance. Length is the first column versus supplement plus dose. We are not considering the interaction here. Okay, so what do you get? The data is the data 1. So summary is, you see that supplement is significant. Both are significant, right? You see that, meaning that the average of different supplement, average tooth length for the different supplement are not equal. Also average tooth growth, okay, tooth growth or the tooth length for different doses are not equal as well. Let us read that. From the ANOVA table, we can conclude that both supplement and dose are statistically significant. Dose is the most significant factor variable because it has a very small p-value there, right? and these results would lead us to believe that changing delivery method, supplement, or the dose of supplement will impact significantly to the mean tooth length, okay, which indicates that the level of the supplement are associated with significant different tooth length. Also, the level of dose are associated with a significant different tooth length, okay. Similarly, if you want to see the interaction effect, so you see AOV length and the supplement plus dose and then plus that column sign in the middle. If you do that, you will see the interaction effect as well. So interaction is also, you see that interaction is also significant. You see that is less than 0.5. So this is also significant, okay. So it can be seen that the two main effects, supplement and dose, are statistically significant as well as their interaction, which indicates that the relationship between dose and tooth length depends on the supplement method. In such case, we ignore the individual effects of the independent factors. So this is very important thing, okay. If you get the interaction effect significant, then we do not go into the depth of the significance of the each individual factors, okay. If the interaction effect is significant, you just focus on the interaction effect, okay. We ignore the individual effects of the independent factors in that case, okay. So let us do the assumption test. You can do the box plot, okay. If you do the box plot, you see that, so what is that orange stands for? So the orange, and let me see what it says, salmon 2 and saddle brown is for supplement and then dose, right? Oh, you know what, I should have given the this is orange juice. So this orange is the orange juice, okay. This orange is for the orange juice, and then this is the vitamin C. These are for the vitamin C, and see, you have 0.5 dose, 0.1 dose, and then dose 2 for the orange juice, and then the tooth length. This is the tooth length, and for the brown one, this is 0.5 milligram. This is 1, and this is 2. Okay, so what you can see from here is, I will do the interaction plot as well, but you can also some guess there, right? You see that oranges has slightly bigger tooth length than the vitamin C. You see that, and also on orange juice, you see that the 0.5 dose has smallest the median, right? Because on the box plot you get the median. Then this is orange juice up to dose 2, because it is bigger than that, okay. Similarly, for the vitamin C, 0.5 is a lot smaller than the dose 2, right? So you can see that, that's why they are all significant. So dose is also significant, and also the supplement is also significant there, okay. Okay, so let me go over this. That was the box plot. So the box plot indicates that there is an outlier in the vitamin C. You see that there is an outlier there. Group with dose 1 gram. Let us not worry about that for now. From the box plot, we somehow guess that orange juice has more effect on tooth growth than vitamin C. You see that orange juice has a higher, okay. When dose is 0.5 and 1. When the dose is 0.5 and 1, you see that the big difference here. But between 1 and 2, the difference is not very big, okay. Similarly, on the okay, for higher dose, it looks like they have the same effect for tooth growth. This may be seen clearly from the plot, okay. Now let us do the interaction, meaning that we will plot the averages. This is what the average look like. You see that those two, so that dotted one is for orange juice, it has a higher average, and then the vitamin C has lower average. You see that, and then they cross, okay. They cross means there is an interaction effect, okay. Let us look at that. The effect of dose on tooth growth is clear from the plot. X factor, the factor to be plotted along x-axis. So this is just the what it is doing is, it is just talking about what is X factor, what is the trace factor, what is response, what is type, all those kind of things. So but what we can see here is that the supplement is also significant, the dose is significant, and then the interaction is also significant. But whenever we see the interaction is significant, we don't talk much about the individual effect of the dose and supplement. Okay, there is interaction effect, meaning that the effect of the levels of one factor, levels of the dose, there is effect of the levels of the dose on the supplement. Okay, that's what we get. Now these are the basically the checking the whether the variance are equal or not. Okay, and then by plot, by the separately. Okay, whether the variance are equal or not on the interaction. Okay, so we got that the variance are equal because we see that the p-value is greater than alpha. Okay, these are the statistical way. And from the plot, homogeneity of variance, by the plot method, you see that that red line is almost close to that. Also, we can see the homoscedasticity. What that means? That means that for each value of x, the data are equally scattered. See, it is also scattered. They are not very much scattered, like very condensed here and then very scattered here. It is not like that. So it is almost the similar everywhere, right? That is what we get. So what we get here is the variance 2 is the normality. If you put 1 here, that will check the variance, and if you put 2 here, that will check for the normality or the of the residuals. The residual versus fits plot is used to check the homogeneity of variances in the plot. There is no evident relationship between the residual and fitted value, meaning sometimes you get like increasing order of that red line or decreasing order. In that case, we say that the homogeneity of variance is violated. Since there is no patterns there, so they are not violated. Okay, so what do I want to do is the statistical method for the normality. We see that it is 0.6694. So the variables are normally distributed. Okay, and if you want to do the graphical method, you see that almost all the data points are close to the normal line. That is the QQ plot. Also shows the normality is not violated. So we see that there was interaction effect, right? There was interaction effect. So we want to see the 2K HSD, and then also there was the block means were not equal, and then the column means were not equal. Also there was interaction effect. So if you see the 2K HSD, and then you see that there are all possible combination. You see vitamin C 0.5 versus orange juice 0.5, it is significant. Another is vitamin C, orange juice 1, orange juice 0.5, also significant, right? Almost all of them are significant. What do you see here? Under pair, 11 out of 15 computer comparisons were significantly different. The average was significantly different. That's what we do. So this completes the analysis of variance for two factors. Okay, so analysis of variance for multiple factors are very complicated, so I'm not presenting on this course. Okay, so it will be a lot of work when you do manually, but you can study because these are the base, right? You can use this concept that you learned on one-way and two-way ANOVA to learn the other types of different cases of two-way ANOVA and other types of ANOVA. Okay guys, thank you very much.